Matthew.
Hello. Hello.
Hi, how you doing?
Good. And I believe I already sent. Yep, there we go.
Okay. Let me graph this in Wolfram Alpha.
Oh, really? I'll do it on my calculator.
Yeah. You're allowed to use your calculator for stuff like this, aren't you?
Yeah, some of them say calculator and some of them say we're not allowed to.
You're not allowed to?
On some, but on this one we are.
Oh, okay. Let's see what this function looks like. Okay. There's the line y. Well, the function itself looks like a normal distribution curve. Jeez, it's been a long day. And what? Y equal 2?
Yep.
Okay, so they want this area from where to where. Find the area of R. Okay, so they're saying that this is bounded by that and that. So first of all,
how do we know where it's bounded? How do we know where it says it's bounded?
well, because it says it's bounded. In other words,
it's that upper part.
Yeah, in other words, I know that this crosses. In other words, it has to be a finite area here. If I had a curve like this and the line y equal 2, I wouldn't be able to take the area under that curve between the line and the curve. Not without having 2 points. They didn't give us 2 points. In other words, they didn't say the area from x equal -5 to +5. Mm-hmm. So we can safely assume that they do intersect at some point. How do we find out where? What is that x value and what is that x value?
I could graph that.
Well, you don't even need to graph it. Just plug in y equal 2 and solve for x.
Mm.
So we got 20 equals 2x squared plus 2. 2x squared equals 18. X squared equals 9. X equals plus or minus 3. So that point is -3. That point is +3. So now it's relatively simple.
The integral from -3 to 3.
So the integral of 20 over 1 plus x squared dx, whoops, what did I forget to do? I forgot to subtract 2. From -3 to 3. That will give us, that gives us this area. In other words, if I didn't subtract the 2, I would have gotten the area between that graph and the x-axis.
Mm-hmm.
But, of course, that graph doesn't ever hit the x-axis, so really wouldn't be able to figure that out. So that's why they put the line y equal 2 in there. All right. Now, to take that integral or to evaluate that integral,
since we're going to use a calculator, we can just plug that in.
that's good because that's a hard one to evaluate.
Yeah, so I got
That's inverse
30.
tangent. The integral of 1 over 1 plus x squared is inverse tangent x.
Mm.
Not that this is 1 over 1 plus x squared, but I could certainly take this 20 outside the integral and make it 1 over 1 plus x squared.
All right, I'm looking at that 37.96. I'm just checking to see if that's what she got. Yep.
Let me open my answer.
Got it right.
The answer sheet. This is just a screenshot of it. Yeah.
Mm-hmm.
Okay. Find the volume of the solid generated when region R is rotated about the x-axis. After we rotate this about the x-axis, what kind of solids are we going to use to slice it and dice it?
Discs.
There's going to be a big hole in the middle.
Oh yeah, what do you call washers? Yeah.
Washers. So what is the area of an individual washer? Let's pick a washer right here. It's got a hole from there to there. Okay?
Would be.
So the area of this washer is the area of the large circle minus the area of the small circle. What's the radius of the large circle?
It'd be the 20 over 1 plus x squared.
Yeah, it'd be f of x, right? In other words, this is f of x. So no matter where we're at on the x-axis, this point here is going to be f of x.
Mm-hmm.
And this point here is going to be f of x. Well, f of x is this function. So I'm going to take the integral, and I want pi r squared minus pi r squared, which is pi times r squared minus little r squared times dx. R stands for radius, so from minus 3 to 3, r squared is 20 over 1 plus x squared. What's little r squared?
2.
Well, little r is 2, so little r squared is 4.
4. No, plug it on my calculator.
Let's just see if she's got the same. Yeah. It's not so much coming up with the cal. You see the way she does this financial or numerical integral down here? In other words, she didn't put in the function. In the calculator, she had already put in y1 was equal to this function.
Mm-hmm.
So instead of rewriting the function, she put y1 squared minus 2 squared instead of f of x squared minus 2 squared. She already had that in the calculator. If the other line was not a straight line, if it wasn't 2 but it was some function, you could define the other function as y2, and then you would take the numerical integral of y1 minus y2, comma x, comma minus 3, comma 3.
y1 squared minus 2 squared.
Which is a much easier way to do numerical integral because it's kind of difficult to put in some of these more complicated functions. And I guess either way you have to put it in. You either have to put it into your y menu or you have to put it in to the numerical integral spot.
All right, I got it. 187.
The region R is the base of a solid. For this solid, cross-sections perpendicular to the x-axis are semicircles. Find the volume of the solid. So here's the base of our solid. So I want semicircles that are perpendicular to the x-axis. I draw one of them. I draw another one. Is that good enough artwork to indicate what I'm doing?
Yep.
Okay, so let's figure out this time, let's do it correct. Now, last time I got a little ahead of myself. I tried to do multiple steps in one. And it's always hard when you're working with semicircles because the radius is half the diameter and the semicircle is half a circle. So you end up dividing by a lot of 2's. And last time I had one too many division by 2's in there. So this time, let's do it the way she did it in your class, which is let's define the diameter and then let's define the radius. So the diameter of each semicircle is what?
Wouldn't it be top minus bottom function?
So that's the diameter. So the radius is half of that. Okay? So now, let me erase some of this other stuff here. So there's the radius. And it's pi r squared. The pi I can remove. This is r, so I'm going to square that whole thing. And it's a semicircle, so I'm going to take half of it. So, what do we have here? We have the same thing as we have over here, only it's minus 2 divided by 2 squared. Now, let's simplify that a little bit. That's what we got so far. Right? Pi over 2 outside the integral sign, the radius squared inside the integrals. Well, after I square that, I'm going to have a 4 in the denominator. I'll take that out also. So I got a pi over 8 out here. And what I'm left with is the numerator squared. That should be the answer. Shouldn't have this page on there?
It's another page, isn't it? C was a part 2.
Okay. Is that her setup?
Let me She has it power 2 from the integral -3 to 3 of 10 over 1 plus x squared minus 1 squared dx.
Okay, if I divide both of those terms by 2, that's what I get. In other words, I didn't need to do it the way I did it. I had pi over 2 outside anyway. And then I have to divide this by 2, that 2 right there. And when I divide the first term by 2, it becomes 10. When When I divide the second term by 2, it becomes 1. So there's my setup. And again, you can do the numerical integral of that if you want. Although that can be done by hand because that's the inverse tangent. The antiderivative of 1 over 1 plus x squared is inverse tangent of x. And I could remove, in other words, I can, the way, if I wanted to solve this by hand, I would go ahead and square it, giving me 3 terms. The only term that gives me difficulty is this one in terms of integrating it, and that's inverse tangent. Well, hold on a second. Maybe it's not inverse tangent because it's going to be squared. The whole thing's going to be squared. Yeah, that's liable not to be so easy to integrate. Because after we square it, we've got a real 3-term denominator that has an x to the 4th in it. So no, that's not going to be easy to integrate. Yeah, a calculator is the only way I know how to do it, even.
All right. That's good as well. I got it.
And again, we're going from -3 to 3.
And then I got 174.68. Which is what you got.
Good.
So that's good. All right. Move it on.
You got any more?
Yep. I just sent you.
I was going to say, you could probably read some of these to me. But that's okay. I can.
I already sent you.
Yeah, I can get it off my. Do you hear all that background noise? Sounds like chatter, doesn't it?
Yeah.
Sounds like it's like we're picking up another conversation. Which I suspect we are. I suspect that's what it is some sort of a data leakage. Okay, should we do one?
Yep.
I think multiple choice doesn't help a whole lot. There's y equal x squared. There's y equal 4. And we want to revolve this area about the line y equal 4. So we end up with a solid that kind of looks like that. Right? It's not really a sphere. It's a parabola rotated about the line y equal 4. So how are we going to divide this thing up?
We got to figure out where the integral's from. So we've set 4 equal to x squared, and I got plus and minus 2.
Okay. We're gonna make it discs, washers, cylindrical shelves.
Discs.
Okay.
I've never heard of a third one.
You haven't heard of cylindrical shells yet? Okay.
Nope.
No, unfortunately, you probably will. They're the hardest ones to even picture. Take a dollar bill out. Take a dollar bill out, rotate it, and have it touch the two ends together, and you got a cylindrical shell. Think of a water tower with no water in it.
That's weird.
A cylindrical shell is an empty right cylinder. In other words, it's empty in the inside, and the skinny edge is the frame of the water tower.
What is that used for? What type of shape would that be used for?
Well, it's used for a number of things, but primarily it's used in the same places where discs are used, but when you want to integrate along a different axis. If your function is a function that cannot easily be written as a function of y, then sometimes you have to differentiate along a certain axis. And if it doesn't fit your disks, it will fit cylindrical shells. Cylindrical shells are always perpendicular to the axis that disks would be used on. But, yeah, let's not make it harder than we need to here yet.
Yeah.
So it looks like we can use disks that run perpendicular to the x-axis. I don't see why we can't. In other words, the skinny section, the skinny part of the disk is dx. So, what's the radius of each disk?
The radius would be x squared.
Well, that's the distance from here to here.
So it would be x squared minus 4 for x squared.
I think it's 4 minus x squared.
Top minus bottom.
Right?
The axis.
Well, the way to figure this out, these are always a little tricky when they have you rotated about a line. But the way to figure it out is if I'm there, x squared is very close to 4, right? The radius is very close to 0. The radius is 0 right there. And that's 0 right there also. And the radius is biggest right there. That's 4. The radius is 4 right there. So that's the radius. So I got pi r squared dx from minus 2 to 2. This one is easy to integrate because if we expand this, we just have a trinomial polynomial, which we can then separate into 3 pieces and integrate each one alone. Okay, you good with that one? Does that agree with hers?
We need to figure it out first.
If you want to figure it out, leave the pi out of it and just do this, because all your answers are in terms of pi. So if you do it without the pi, whatever number you come up with, it's going to be one of those numbers.
Alrighty.
The coefficient of pi. Now see here, you could put y1 in as equal to 4 minus x squared, and then when you define the integral, you would just say y1 squared.
Oh, she used a calculator on this.
Yes. Is that what you're doing?
Oh, no, I wasn't. I was doing it by hand.
Well, it can be done by hand, but it's not so much the answer we're interested in. It's the setup.
Yeah.
As long as she's got it set up exactly like this, then we can probably go on.
Yeah, that's what she has.
Okay. All right. These regions are not easily integrated along the x-axis. Notice why. How would you define the radius of that disk?
Yep.
If I set up a disk perpendicular to the x-axis, not a disk, we're doing area. So if I set up a rectangle, how do I figure out the height of that rectangle right there?
You can't really.
You don't. However, notice that if I divide this area up into horizontal rectangles, everything works. It's the right function, which isn't a function. I should say it's the right relation minus the left relation. Integrated from bottom to top. Okay? All right. So in order to do that, we have to define this function as a function of y. Well, how convenient. They've already done it for us. Notice that if I wanted to integrate that vertically, I would have to have a function of x. And I can't get it. I can't solve for y as a function of x. So this would be very, very difficult to integrate vertically. But piece of cake to integrate horizontally because both functions were given to us as functions of y. So that function is the one on the left. This function is the one on the right. So we go right minus left. Just like if we were integrating the other way, we would go top minus bottom. So we're going to integrate.
Looks like negative 1, 2.
Well, we have to figure out where the intersection point is by setting these equal to one another and solving for y. Remember, we're integrating along the y-axis, so it's going to be a dy. So our limits of integration have to go from the y-coordinate to that y-coordinate. Well, if I set the x's equal to one another, which I can certainly do, this will allow me to solve for those 2 points. Let's see, if I bring that y cubed over, I got y cubed plus y squared minus 4y minus 4 equals 0. Notice I can solve that by grouping, which is rare. Let's solve that before we go any further. Do you know how to solve that by grouping, or do you even need to know how to solve it by grouping? Or can you just put that in your calculator and come up with values for y?
Yeah, I got negative 1 and then 2.
Negative 1 and what?
And 2.
And 2. So this is the negative 1, and there's 2. Actually, they gave them to us. I wasn't looking at the figure. So we didn't have to solve for it, but we could have. So now I'm going to integrate from what to what?
Negative 1 to 2.
And I'm going to integrate this function minus that function. which gives you minus y cubed minus y squared, no y, 2y minus, oops, plus 2y minus a minus 2y is plus 4y.
Mm-hmm.
And then 4 dy.
And then I just plugged that into my calculator.
Okay.
And I got 11.25.
Okay.
So B. And I'm checking. Yeah, that's correct.
Okay. I always like to draw a picture. Because for one thing, you're not sure which is the above function and which is the below function.
Mm-hmm.
Well, y equal x minus 2 goes through the y-intercept, has a slope of 1. So there's our figure. And y equals 0. So this is the area that we are rotating. Okay?
Isn't that I'm going to need washers and discs?
Yeah. Yes. In other words, we're going to end up with a figure that looks kind of like that. Solid. So we can do it two ways, actually. We can use, and I actually like doing it in 2 steps rather than 1. I'm going to tell you why. From there to there, we can use discs. From here to here, we got to use washers because we're going to have a big hole where this little indentation is here. In other words, if we tried to make this solid with a bunch of washers and discs of various radiuses, I could use discs on this part of it, but then I'd have to use washers over here. Well, this point right here is 2. So let's just integrate it.
So the pi times the integral of 0 to of top minus bottom, which would be root x minus 2.
Actually, just root x
Oh, yeah.
squared. Remember, that's the radius. Dx plus, in other words, that's going to be this part of the volume, plus the integral from 2, where do these intersect? Where is the square root of x equal to x minus 2? Okay, so this point is 4. So now we're going to integrate from 2 to 4. And we're going to integrate...
And this time it's top minus bottom.
Right. And this time it's washers. So it's pi r squared minus r squared.
So the root x squared minus x minus 2 squared. Yes.
Excuse me, 2 to 4.
Alright, now I'll plug all that in.
Does she, in her key, does she do it all in one step?
Probably. I'll look though.
You can do it all in one step. The thing is that the inside radius in this step is 0. And the inside radius does not take on any positive values until you get to that point right there and go to the right. And then you have an inside radius that's defined by x minus 2. So I'm not sure how you do it all in one step, to be honest, when you have to use, even if you used washers the whole way, the inside radius changes from 0 to 2 than what it is from 2 to 4.
Yeah, she just did it. She figured out she flew the same exact thing, so the same set.
Okay.
It was one step.
So is this correct, the way she, does this match what she did?
Yep, exactly.
Okay. That's it for this page? Did you send me another page, or?
Here, I'll do that.
Okay. When's our next session? We have a session tomorrow? Yeah, tomorrow.
Mm-hmm. So I got a big test on Tuesday.
Okay.
Alright, I just sent it. It might take a little bit.
Ooh, I think I just got a spam email. No, it didn't come in there.
I sent.
Can you verbalize it?
Yeah, I'll go with 5. I'll verbalize that one. That one's short. Find the area of the region enclosed by y equals sine of 2x and cosine of x. From negative pi over 2 to pi over 6.
Okay. We kind of need to graph these, because otherwise we won't know what the above function is and what the below function is.
Mm-hmm.
Let's see what happens if I graph two functions at the same time. Y equals sine of 2x and y equal cosine x. Okay, well the blue line is the 2x. Purple line is the cosine. We're going from minus pi over 2. Okay. To pi over 6, right?
Mm-hmm.
Fortunately, I don't know how to put this in radians, but does it matter? I don't think it matters. Minus pi over 2 is about minus 1.6. So from looking at the curve, I can tell that it's in this area here. So from here to here, the cosine is on top. From there to there, the sine is on top. But that's way beyond pi over 6. Pi over 6 is somewhere in there. In fact, we need to figure out that intersection point there. So
can I just set this up easily? My calculator would be from negative pi over 2 to pi over 6 of cosine of x, since it's on top, minus sine squared of x?
no, because I don't think it's on top in that whole range. Maybe it is. I'm going to have to look. In other words, that would be correct if
cosine was on top the entire time.
Yeah, the problem is, what is this point right here? Because everything to the right of this point, the sine's on top.
That right there is pi over 6.
That is pi over 6?
Yeah.
Let's see. Cosine of pi over 3 is equal to the sine of pi over 3? I don't think so. If I solve sine of 2x equals cosine of x, let me enter another Wolfram alpha so I don't lose that curve. Sine of 2x equals cosine of x. Okay. Yeah, you're right. It is pi over 6. This one right here, when n is 0, it's just pi over 6. Okay. So that's nice. That means we know cosine is on top the whole way. In other words, from somewhere in here, cosine is over sine, and it's always above it until we hit that right limit. So even if we were going further to the right, we would have to do this in pieces. In other words, we'd have to do the first piece from minus pi over 2 to pi over 6. And then we'd have to do the next piece from there to there with the sine on top.
So that right there, that integral that we had was correct. That was it.
Yeah. Do you know how to integrate sine 2x?
Yep, I just plugged in my calculator.
Okay, that's fine. And let's see, there's no pi in front of this. These are just rectangles.
Alright, here's another one I can tell you. The area enclosed by the curve y squared equals x times 1 minus x is given by, and then you gotta figure out.
What?
Y squared.
Hold it. Why are you squaring them?
Oh, this is the next question.
Oh, I'm sorry. Oh, we're done with this one. I thought we were working on how to do that integral, yeah. You know the integral of sine of 2x.
That would be cosine of 2x over 2.
Minus cosine of 2x over 2.
Oh, yeah.
Because the derivative of that is sine. All right. I got it actually here. I got your email.
So we just did 5. Because 4 was too long. So
Okay. So
I guess we can do 4 now.
Let's do 4 now.
Mm-hmm.
Which way do I have to turn this? I guess always to the right. Okay. Let's draw a picture of it. The inverse sine is just the sine curve reflected about the line y equal x. Okay? So if I have the line y equal x, and I reflect this thing from minus pi over 2, then it looks like hold on. What does it look like?
It was like the first time we've done inverse sine.
Yeah. So it looks like that. That's the curve, inverse sine. And the vertical line x equal 1, we'll assume that that's somewhere there. And the x-axis. Okay, so this area here is the base of our solid.
Mm-hmm.
And for each solid, we've got cross-sections that are squares perpendicular to the x-axis. So I'm going to put a square on here. The skinny side of the square is dx. In other words, this square is sticking out of the page at us.
Mm-hmm.
So the area of each square is what?
It would just be the area of the square is sine of inverse sine of x squared, right?
Correct. In other words, that's the side length of each square. So the area of each square, the area of each square is 0. And we're going from first quadrant only, so we're going from 0 to
1.
Yeah, but where is the inverse sine equal to 1? Pi over 2. Ah, hold on. Hold on a second.
Wait, no, isn't it just a 1? We're doing the x value.
You're absolutely right. You're absolutely right. So it's from 0 to 1. In fact, that should be it.
Alright, now I plug that in my calculator.
That's another one that would not be easy to integrate.
No.
I could integrate inverse sine. I know what that is. But I'm not sure what the inverse sine squared integrates to.
I got 0.467, and that is C, and the answer is C.
Okay. y squared equals x times 1 minus x, which means y equals plus and minus the square root of x times 1 minus x.
And it looks like now the answer is they distributed that.
Well,
X minus x squared.
notice that this, if I had y equals plus or minus square root of x, there's the plus square root of x, there's the minus square root of x. So if I found the area under the plus side, I would multiply it by 2 to get the area of the whole thing.
Mm-hmm.
So let's take this plus or minus, make it a plus because I can integrate that. So I'm going to integrate that from, what, 0 to 1? Must be 0 to 1. They're all 0 to 1s. And multiply it by 2, which looks like answer A.
How do we get the x out of that?
Doesn't look like answer A. Excuse me, it looks like answer B. If I distribute this, it's x minus x squared. Yeah.
Plus or minus. Alright, yeah, I understand that one.
Is B the correct answer?
Yep.
Okay.
We can probably get one part of this next one done. This one has to be, I have to see the picture of this graph.
You have to send me a picture of this one?
Alright, I just sent it.
Okay. I get rid of all my windows here I don't need open. What's the next one concerning? Is it area between the curves or?
Yeah, that's basically what it is.
Okay. Internet must be slow tonight.
Yeah. I think I might be able to just say it. It's a graph, but it also gives me the equations of the lines. So it says that R be the region in the first quadrant enclosed by the graph, so y equals 2x, and y equals x squared. And then just the first part is find the area of R.
Okay, there's those two curves. My thing just came in here. So the area of R is just the top function minus the bottom function.
Mm-hmm. The integral from 0 to 2 2x minus x squared dx. So integrating that, it'd be x squared minus 1/3 x cubed. And then from 0 to 2, so we start putting a 2, should be 4 minus 8/3. I believe. I'll check that's what she got.
Okay. So, should we look at B?
Yep.
Okay. For this solid, we're going to put cross sections on top of that area. They're going to be perpendicular to the x-axis. And they're not telling us what they are. They're just telling us what the area of each cross section is.
Oof.
That's fine. That's beautiful. We don't have to figure out anything more. They're telling us that's the area. So that's pi r squared.
Oh. So we can integrate that from 0 to 2?
Yep.
Oh. So that's
Let me think about that for a second. I haven't seen a problem like this before. Let's just see. So this comes up and hooks it there. So here's our solid. Well, if we knew what type of object was on top of there, we would take the integral from 0 to 2 of the area dx. The area dx, right? Now normally when we were dealing with semicircles, the area was pi 1/2 pi r squared. We had to figure out what r was and find out the area by squaring r. Well, here we don't have to do that. They're giving us the area. So the only thing I need to stick in that integral is sine of pi over 2x dx. That should be the area of that solid.
Mm-hmm. And then the antiderivative of that would be negative cosine of pi over 2 over pi over 2.
Yep.
Integrate that with 0 to 2, alright. Sounds good.
Let's talk about C, since we're almost done. Another solid has the same base, only in this solid we're going to use cross sections perpendicular to the y-axis. And they're going to be semicircles, right? But do not evaluate an integral expression for the volume of the solid. So which axis are we going to integrate along?
The y.
Okay. So to integrate along the y-axis, we're going to need a function of y. Oh, no, yes. Oh, we're not using this. We're using semicircles. So, in other words, the wrong one. If this is my base, and I'm going to use semicircles perpendicular to the y-axis, each semicircle is going to be like that. So, what's the diameter of each semicircle?
It'd be right minus left, each one squared.
So what is the right? X squared?
X squared
Minus
squared.
2x? Hold on. Let's do it one piece at a time. I mean, that's how I messed up the other time, was trying to do it all at once. So is that the proper diameter of each semicircle? I think it is.
Mm-hmm.
Was that our two functions? Yeah, x squared and
Yep.
Okay. And it's definitely x squared minus 2x, not the other way around. So the radius is x squared over 2 minus x.
So then
You see what the problem is already? I've defined my radius as a function of x.
Oh, and it's in y. So we got to switch the equations around.
So if y equals x squared, then x is equal, we're first quadrant only, so I can just say square root of y plus. And if y equals 2x, then x equals y over 2.
Mm-hmm.
So my right function is this one. My left function is that one.
Mm-hmm.
So the diameter is equal to square root of y minus y over 2. My radius is square root of y over 2 minus y over 4. So I'm going to use semicircles. So I've got a pi over 2
Integral from
times
0 to
this
4.
squared dy. From 0 to what?
Correct.
4. Not 0 to 2, but 0 to 4. Because we're using the y coordinate.
Uh-huh. And I'll see. That's a sheet. She said the same thing.
Okay. Let's call it an E.
Oh, we don't even have to solve it.
What's that?
We don't even have to solve it. Just write it, but then evaluate it. So that,
Yeah, you don't have to evaluate. You just have to put the expression. Yeah.
All right.
Matthew, I will talk to you tomorrow night.
All right. See you then.
All right. Bye-bye.
Thank you.
Sure.